So if we generate a narrowband FM or narrowband PM approximation, we know that those are not actually going to contain all of the information, right? This was a subject of a previous video series, was that the narrowband approximation for angle modulation did not quite contain enough frequency components. So therefore, we can use some additional stages to convert this to a more wideband signal. And we can do that with a frequency multiplier. Frequency multipliers work by increasing the frequency, but while you increase the frequency, this is actually also going to increase the frequency deviation. When that frequency deviation increases, you're going to be going from more of a narrow band up to more of a wide band. So frequency multipliers both increase the frequency, the carrier frequency, but also the frequency deviation. So it makes them more of a wideband signal. So this is good because that will contain more of our information if it's more wideband. So how do we do this? How do we make a frequency multiplier? Well, we can use nonlinear devices. So recall, right, our nonlinear device, we could put an input xt in, and at the output, we would get some something that might look like this. So it has some higher order terms in it. So a nonlinear device like this, which we saw previously, you could put in some input and the output's going to contain some higher order terms. So what happens if we put in a narrowband FM signal in? What would happen? So at the output, we would get some higher order term, right? It would go from this cosine only up to some higher order cosine wave term. So that's going to add some higher order terms, and we can see that if we were to convert this, right, so if we were to use some trigonometric identities, right, we could convert this into cosine only terms, and we see that this one would be DC only, and this term is a cosine wave, not squared, at a higher frequency, 2 times our carrier frequency. So this is multiplied the frequency, the carrier frequency that we're at, and it's reduced the amplitude a bit out front. So if we had a nonlinear device and we included all of the terms, right, we would see that there would be many other various higher order terms, right? So if we had a nonlinear device, it could generate any one of these, any number of these terms, right? Each one of these coefficients would be increasingly smaller, whereas the X input would be moved to higher and higher powers. And then when you filter at the output, you could get whichever term that you're most interested in. So that's what we just saw, that you could filter it at the output. So if we were to do this, we could put in our wave. All right, this is our FM, narrowband FM wave, and we could filter at whatever frequency we were interested in. So we could filter it to omega c, and that would give us this one term in particular, right? We could choose to use a filtering system, but we pass it through a nonlinear device, use a filtering system, and we could be selective and choose the outputs that we get. So the spectra for the output on this, if we had this filter at 2 omega c, would be centered at this, but in addition to that, the frequency deviation would also be doubled, right? So this term has also doubled. So not only would a nonlinear device like this double the frequency that it's working at, but it also double the frequency deviation, which is basically the same thing as going from, right, narrow band here, right? This is our narrow band signal, out to a more wide band, right? This signal has 2 times the deviation as this signal, because we see that it goes from coefficient of 1 to a coefficient of 2. So the nonlinear device can both increase the frequency and also increase the frequency deviation. So it leads to a more wideband signal. So we can generalize this to any nth order nonlinear device. So you could have a nonlinear device, right, that works at any n order that you choose. So you go through the nonlinear device and you filter at whatever n times your carrier frequency is desired, and that is going to give us a spectra that's now centered at your nth order, so 2, 3, 4, etc. And it's also going to increase the deviation by n as well. So you can use the nonlinear device to increase the frequency and also increase the deviation there. So you can use these devices additionally in Cascade. So each time that you cascade these devices, this is going to both increase your carrier frequency, right? You could increase this carrier frequency first 2x, then 2x again, then 3x. So 2 times 2 is 4. 2 times 2 times 3 is equal to 12. So if you cascaded these, 2 times 2 times 3 is equal to 12. So that would both increase this to 12 omega c, but it would also, right, we would also add in a 12 here at the output. And so by filtering there, you can cascade these devices, filter at your desired multiplication, and that would result also in a multiplication of your deviation. So your output of this set of nonlinear devices in Cascade would be 12 times your original carrier frequency with a 12 times deviation. So you've made this 12 times larger bandwidth. So you can go from a narrowband signal to wideband signal using these multipliers in Cascade.